coordinating this project. This project, Josephine project, which just as a reminder, involves groups from CSIC in Spain, from University Complutense de Madrid, also in Spain, from München University in Germany, from Chalmers in Göteborg, and CNRS and Thales in France. And today we have the pleasure to have as a guest Dr. Salvatore Mesoraca, who is a Thales research engineer, Thales researcher at Thales Lab, or TRT, Thales Research and Technology, and is a member of the joint lab Laboratoire Albert Fer, together with the CNRS. So Salvatore, before being an engineer at Thales, got a master's or an engineer degree in Torino, and then he moved to Cambridge University for a PhD in the group of Jason Robinson and Mark Blameyer. And then after his PhD, we were lucky to hire him as a postdoc in our group at Laboratoire Albert Fer, and then he became staff member of Thales Research and Technology a few years ago, and since then he has been developing this, among other things, he has been developing these quantum antennas based on high-density pressure superconductors, which he will be telling us about today. So before I give the floor to Salvatore, it's an honor and a pleasure to have him today, and I'd like to invite the attendees to keep track of their questions and save them for the end of the presentation, where you will be given the opportunity to ask questions to Salvatore. Okay, so now, Salvatore, thank you very much. The floor is yours. Please go ahead.
All right, thank you so much, Olivier. Thank you so much for the introductions. And thank everybody for being here. Let's just start this seminar on high temperature superconducting quantum interference antennas. Before we start, just a quick reminder of what I have said about the laboratory where I work on. Is the Laboratoire Albert Fer, is a joint lab between the CNRS, so the National Research Council of France, and Thales, which is a company that focuses on, among things, about defense applications, aerospace, communications, and whatnot. We are located in the outskirts of Paris, just a 45 minutes train ride from Paris. The lab was founded in 1995 by Alain Friedrich and Albert Fer. And as I said, it's a joint lab between these two institutions. We work together, we share equipment, we share fundings, we share ideas. We focus on fundamental research and at the same time also more application side, all of this all together. The research area span from spintronics, obviously, because the founder, Albert Fer, one of the founders, Albert Fer, got the Nobel Prize for actually inventing spintronics in the early 90s. So we got the Nobel Prize in 2007. So obviously we focus on spintronics in the lab, but not only, we focus also on functional oxides, neuromorphics, and superconductivity, which is in bold on my slide because it's what I'll be talking about today. Specifically in the lab, we do a lot of research on this topic. It varies from seeing how superconductors behave together when they're meshed with other materials like ferromagnets, ferroelectrics, 2D materials, to study the interplay with these materials, which sometimes they are antagonists with each other, especially ferromagnets and superconductors. In a recent paper, we just showed how, regardless of their antagonistic behavior, they can actually work together to enhance some kind of properties for the superconductors over a wider, a very long range of effects. We study superconducting electronics. For example, we develop resonators for MRI applications. And for more on the application side, we develop demonstrators with the superconducting electronics in order to make, for example, high-efficient RF filters, and what will be the topic of today, quantum antenna based on high-temperature superconducting squids. course, let me talk about the team and thank each one of them. This is the Supra team, so it's a very large team, as you can see. Most of the people, they've left, some have joined, but I'd like to thank all of them. And the people involved in what I'll be talking today are the big faces that you see on the top right. And I'll take advantage of this slide also to thank the collaborators that spent from C2N to EastPCI in Paris. All right, let's see the outline of the talk. The outline will be starting with an introduction on superconductivity and Josephine junctions. I'll be talking about the London equations. We will be deriving the Ginzburg-Landau theory. We'll be talking about the PCS. No, I'm joking. We're not going to do all of that. It's just going to be an introduction on the few concepts that are going to be needed to understand what I'll be talking about. And it's just that everybody's on the same page. There's going to be no derivations of complicated theories, don't worry. Then we're going to be talking about the actual topic, which is the quantum interference antenna, introducing it and discussing about the working principle and the motivations behind it. Obviously, the applications and for good measure, some fabrications and the recent results that we got in the lab and the mandatory conclusions. Introduction. Let's talk about the superconductivity, which is the main topic of the rest of the seminar. Well, discovered in 1913 by Ons, in 1913, yes, he got the Nobel Prize for it. And it's actually the property of a material to lose its resistance, actually completely dropping to zero, whenever it cools down a certain temperature that we called since then critical temperature. Since then, there's been a lot of development, all right? Mainly the BCS theory, which was awarded in 1972 the Nobel Prize to the Bardeen, Cooper, and Schiffer trio for their discovery, for their formulation, actually, which is actually the base on how a superconducting behaves. And this electron-phonon-mediated interaction that create Cooper pairs, and which are the main characters and actors in this beautiful behavior in solid-state physics. Just to say something that is sometimes forgotten, resistance superconductivity is not just the drop of resistance to zero, but also the Meissner effect, meaning that the superconducting material will expel any magnetic field. I'll say it because it's going to be important for the rest of the seminar. And since then, there are going to be even more Nobel Prizes, even more discoveries, especially the Javier and Josephine tunneling effects in superconductor, which actually opened the way to make devices out of these interesting materials. In 1987, I think the highest, the peak of the interest in this kind of materials was the discovery of a high-temperature superconductor by Bernard Müller. They found what was called then a high TC superconductor with a TC of 30 Kelvin. And that sparkled, as we will see in the next slide, a lot of interest and a lot of new development in material science. And for good measure, two more Nobel Prizes on the topic, on the studies and the contributions on theories to Jens and Ginzburg and Abigazov and Leger. So a lot of interest. Actually, I should update my slides because the Nobel Prize of last year is somehow indirectly involved in superconductivity. So I should also add that prize. So this slide just to say that it's been a lot. There's been a lot of discoveries, a lot of interest in these materials, thanks to their properties. And I said the height of the interest for this, I think it was 1987, because in 1986, in June, the duo Bednorz and Müller in Zurich, they discovered the high TC superconductors, the LBCO, with a TC that was way higher than what usually was discovered up in 10, which was around 10 Kelvin. Their material was about 30. And it sparkled this race that we could see on the previous slides, this race to actually get even higher by the month, actually, not even by the year, by the month to actually get even higher TCs. And actually culminated with the discovery in March 87 of YBCO, who actually was the first material above the boiling point of nitrogen, which was a huge change because we could stem away from the liquid helium technological processes to measure these devices to nitrogen, liquid nitrogen, which is much better, much more economical, way more practical. So it sparked a lot of interest. You can see in New York Times front pages, Time magazine features. And something that I really like is the Woodstock of physics, the so-called Woodstock of physics, because in the 1987 APS March meeting, the news of this discovery of YBCO was so recent actually that there was no planned session at that meeting. So they had the in situ impromptu schedule one for the after session, after the schedule of the day, with a session that ran from 7 p.m. until 3 a.m. and which is available on YouTube, and I highly recommend everybody to go and have a watch because it's pretty interesting. So a lot of interest, and it's just a way to say that it's a very rich field of research. Now we're going to be talking about the next in the seminar about this main brick, which is the Josephine junction. And you can see a Josephine junction, it's a basic element because we have two electrodes separated by a barrier. The barrier can be anything you like. It can be an insulator. In that case, you will have an SIS junction, the so-called SIS junction. It can be a metal, so it could be the SNS junctions, N stand for normal metal. Or you can also have a weakened superconductor, so either the same material superconductor, obviously, or a different one, just with a lower TC with respect to the electrodes. And if you look at the Gismund-Landau order parameter that defines the Cooper pairs inside these two electrodes, they are defined by a certain phase, obviously. And what happened is that the phase difference between these two electrodes, it can actually be, there could be a phase difference between these two electrodes. And what's even more interesting is that if that is the case, what is predicted by the Josephine equations is that there's going to be a supercurrent flowing in this device, okay, with no dissipations of, with no dissipation whatsoever. There's going to be no applied voltage and just the flow of current. So the characteristic IV voltage, you can see it here on the bottom right, where you have the flow of the current with zero dissipation. And whenever we overcome the limit or the so-called critical current, we pass from the superconducting regime to the normal regime. There is another interesting effect happening, that is whenever a voltage actually applied, the phase will actually vary in time. But for us, it's really important to take note of this constant here, which is called the Josephine constant. And it's going to be important for later on, so I'll ask you to keep note of it. And remember that it's around 500 terahertz over volts. Now, it's important to see what happens to these kind of junctions whenever we apply a magnetic field, because even more interesting physics will arise from this. So whenever we apply a magnetic field to this junction, what happens is that the actual phase difference will be dependent on the flux threading through this junction. So that means that the flux will make the phase to vary spatially across the junction. And since, as we saw from the previous equation, from the DC Josephine equation, the critical current will depend on the phase, then actually the current becomes spatially varying with the flux. And it's very interesting because whenever we apply at zero flux, well, there's a current that flows from left to right in an uniform way. Then whenever we start increasing the field, and hence the flux, we see that even more interesting stuff happens, especially at an integer number of the flux, which is phi naught, the flux quanta, because we can see that there is a certain amount of current which is flowing from left to right, but exactly the same flowing right to left. So at the end of the day, canceling each other, making the current flowing zero. If you develop the equations, you actually find out that the equations governing this behavior is a perfectly absolute value of the sinc function, basically a Fraunhofen pattern. And you can see the behavior is actually depicted in the graph here, where the points here that are exactly the specially resolve the images here of the current. So whenever we are at zero flux, we have the maximum of the current, a uniform current. And whenever we increase the flux threading the junction, it will actually drop to zero whenever we have an integer number of the flux, and then rise up to another maximum, which will be lower than the other ones because of the distribution of the current along the axis. So this is just to say that the junction itself does this basic brick element of these superconducting materials is already dependent on the flux. It's already dependent on the magnetic field. as is showed by this graph, where we see that the critical current, it changes by the applications of a magnetic field across the junctions. So it can be used in a certain way to double check if whatever you're measuring, whatever your junction is, just junctions, for example. It can be a way to prove that your junction current distribution is uniform if you get this Van Hoffen pattern. But it's also a way to say that it's a device that is sensitive to the magnetic field. And talking about sensitive devices with the magnetic field, we have to talk about squids, which is the next step of this evolution of these kind of devices. And in this case, we make a simulating loop, you can see on the left, and we place two junctions on each side of the arms of this loop. That's called a squid. It's a superconducting quantum interference device. And it actually relies on the Josephine effect, on the Meissner effect, and on the quantization of the flux. All this to say that if you apply a current that will flow into the arms, we split into current bias divided by 2 and current bias divided by 2 on the left and right. There will be, if you apply a magnetic field, there will be a screening current. That's because of the Meissner effect. Remember, a superconductor will try to expel the magnetic field because it's more energetically valuable to create that current than actually losing the superconducting behavior, because the magnet will try to break the Cooper pairs. So there will be this screening current that would actually add in one arm of the squid, and it will actually oppose on the other one. Okay, and of course, while we increase the flux, there will be an increased amount of screening current up until an half integer of the flux, because then in that case it's more energetically favorable to actually switch to the next integer. So you see that whenever we measure the voltage across this device, it actually oscillates between a Vmax and a Vminimum. And that is because we're actually, with the current, is actually oscillating with these two states between a positive integer and a half integer all the time, while you increase the flux. So what I just described here, if we just take this response of the voltage with an applied magnetic field, well, I just described what it is actually a transducer, because now if we focus on this linear regime here, we have, for a very tiny change of magnetic field, we have a larger response in voltage, which is usually in the range of the microvolts, so something that we can easily measure in a lab. And what I just described right now, it's one of the most sensitive magnetometers that exist on the planet. We use it for many applications that we will see later on. But I'd like you to remind two important things. One is that this conversion factor, this transfer factor between how we can convert the magnetic field into a voltage is in the order of tens of volts per Tesla. That is dependent on the critical current. It is dependent on the normal resistance of your superconductors. And of course, it also depends on a few more complex variables like the inductance of the loop itself. Another important things to keep in mind is that the periodicity of this response, it actually is inversely proportional to the loop area. So if we change the loop area, we change this periodic response. So very sensitive magnetometers, one of the actually the best that exists nowadays. But it has a limitation. The limitation is that this periodic response, it does not allow us to have an absolute measurement of the magnetic field, because for the same voltage, we have different magnetic fields. And we are obliged to have a feedback loop in order to always be in the linear regime whenever we overcome this linear regime in our measurements. So it limits the functionality of this magnetometer to frequencies up to 100 megahertz because of the electronics needed to be used for an efficient operation. So as that is a very common sensor, is used in many applications. That is actually the reason why there are so many suppliers and so many manufacturers in the world. It is just a list which I'm sure is not extensive, it's not exhaustive, there are many, many more. But you can see it spans from the US to Japan, to China, to Finland, and of course to France where we work on them. And these can be either commercially available or just like groups and research labs working on them, developing them for many applications. That again, we will be seeing in a bit. There are certain techniques to improve how a squid behaves, how a squid is actually performing. We can have arrays, series of arrays where we actually chain together squids of the same type in order, for example, to increase the delta V max. So delta V max is the height of the oscillations, for example. We can actually do that to increase also the transfer factor to have it even higher. We can do 1D parallel arrays, or we can do a combination of both. We can do 2D arrays. And here in the table, you can see how it actually, the properties scale with the number of squids. Obviously, this is said only if we consider that all these squids they have to be on the same, especially the junctions, but especially the area. The area has to be exactly the same. There is a case where actually making a 1D series array of squids with different areas actually is an improvement, or anyway, something different. And that actually is the superconducting quantum interference filter. So the next building block of our seminar. It's what is called a KIF. So in this case, instead of having the squids, so it's a squid array, but instead of having the squids of the same area, we have them with different loop areas. Okay. And if you remember, I said that the response, the periodicity will change with the area. So here we have the different responses with different periodicity. And you can see that for fields which are far away from zero, we have this non-constructive way of adding up this response, these sinusoidal responses. While at zero, all these mina will add together. So the end results will be this response. So that's the typical response of a SCIF device, is the purple curve. So we got rid of the periodicity. We have actually obtained this very high linear B regime where you can actually use it as a transducer again from voltage, from magnetic field to voltages. And you see the increase in transfer factor. It's pretty considerable, because now we're talking about transfer factor of the order of tens of thousands of volt per Tesla. That means that a very tiny change in magnetic field will now correspond to a very large voltage change. And we're talking about millivolts in this case. So millivolts are even easier to measure with a certain accuracy. So it actually becomes a very sensitive magnetometer. All right. So the original name for this device was called, the first time I think it was called the superconducting array, so SQA. Then it becomes superconducting interference filter. Filter, it's a name that was given by the group in this paper, just because it resembles the response of a stop band filter, you know, with the response here. But actually, it has nothing to do with the filter. It's a bit misleading as a name. That's why we prefer to call it in a different name, actually a more catchy name, which is the quantum interference antenna. But why antenna? Well, let's talk about antennas, because it's going to be part of the talk. Antennas. Well, antennas, classical antennas, as you all know, they all rely on the electrical resonance. So you have the electrical component of your electromagnetic wave. So we'll actually make oscillating, we'll create a standing wave in the electrons oscillating in the rods of your antenna, and hence generating a current that will be collected by the receiver. So they are limited by a few things. First of all, the size of the antenna needs to be proportional to the wavelength in this case, in order to have the standing wave in the rod. And they work really, really well. That's why we use them in many applications, but they only work in a narrow band. So in the band we're actually designed for. And this is not an issue whenever we work in very high frequencies. So whenever we have wavelength in the orders of centimeters or meters. So FM radio, TVs, that's why we have this, we used to have these antennas either at home or on our cars, because by changing the size, we could actually change the frequency that we were able to detect, to work with. But whenever we increase the frequency, you see, whenever we get to the very low frequencies or the extremely low frequencies, you see that the size, the characteristic size of these antennas, it becomes unreasonable. We get to the kilometers, the hundreds of meters. It doesn't make any sense. There is no way. And actually has a series of implications. You can see, for example, if there's a submarine that is obliged to actually pull in the water a wire antenna, which is sometimes long up to 600 meters, just to allow itself for communications in the very low frequencies. On airplanes, you have these rods, which are actually there for antenna purposes, together with other small antennas, again, because each one of them will be corresponding to a certain frequency. The same applies to these trees antennas that resembles a bit the ones that we used to have in our homes. And again, all the reasons of this is because every single rod will actually be resonating at a certain frequency and one frequency only. So the classic antennas, they actually have this drawback of actually being narrow banded and being limited, especially at low frequencies for their size. And just for an exercise for you, I'll let you count the number of antennas that you can spot on this big boat from the French Navy. But let's go back to the skiff then. And first, let's talk about the electromagnetic wave. The electromagnetic wave is, as we all know, is an oscillating electrical field, but also a magnetic field. And we just saw that a skiff, so a quantum antenna, is actually sensitive to the magnetic field with a very high sensitivity, actually. And more importantly, if you remember the Josephine equations that we seen at the beginning, and I asked you to remember the Josephine constant of almost 500 terahertz over volts. Well, now if you can define the some kind of critical frequencies, which is the Josephine constant times the critical voltage of our skiff, which is in the order of millivolts sometimes. Well, we find that this critical frequency is up to the gigahertz. All this to say that the physics behind a skiff is actually true from DC up to gigahertz. So that means that we can detect, we can use a skiff as an antenna to be sensitive to the magnetic component of an electromagnetic wave, regardless of its frequency, because again, we can go from DC to the tens of gigahertz. The working principle will be the following. We have the skiff here at the center, all right, in this curve here. It's the typical response, the voltage against the magnetic field. It's the skiff which is going to be polarized in its best operating conditions. That means the best the best temperature, the best current, and the magnetic field that gives us the best transfer factor. That means that the best slope here. So whenever we inject an RF field, so an electromagnetic wave, the oscillation of the magnetic field will actually be transformed into an oscillating voltage that, again, it will be in the order of the millivolts, and it's going to be easily measurable in a lab. And by just a signal treatment, we can retrieve information on whatever electromagnetic wave we were sending into the skiff. So that's the basic idea of an antenna, of a superconducting quantum interference antenna. And the motivation behind it is pretty straightforward, because again, it's an ultra wideband sensor that can go from DC up to gigahertz. It's pretty compact because it's just a little sample that can fit on the top of your finger. All right. And I haven't talked a bit, stressed on it too much, but actually we are sensitive to the magnetic component that threads perpendicularly the squeeze area. All right. So that means that we can actually be adding another step of important things about this antenna, which is the directionality, because if you put like 3 of them in a granulometric wave, you can actually detect the directionality of the electromagnetic wave. So pretty interesting. That's the motivation behind it. But of course, it comes with a drawback. It's made of superconductors. There's no way around it. We have to cool them down. But if you go back to the table that I showed at the beginning with the exponential, well, it's even higher than an exponential because it's almost a vertical race to get to the higher temperatures. We can get away with this fact that this drawback of cooling down. We can get away with it because we can use YBCO, and that's the material that we chose to work with, because its TC is around 90 Kelvin. And that means that we can use machines that have a reduced cooling power. What do I mean by that? Is because if you look at the system that usually needed to cool down low TC superconductors, so in the range of 4 Kelvin or even lower millikelvins, we are obliged to use very big machines, very heavy machines, but not only on volume and weight, but also on the energy side, on the energy consumption side. They consume from 3 kilowatts to 8 kilowatts. And as I said, they have a big swap factor, so they are big machines. But what instead, if we focus on high TC superconductors, then we can think about using these small miniature compact cryocoolers that actually fit on the top of your hand, on the palm of your hand. You can see here is one example. This is a cryostat that is developed by Thales Cryogenics, which is a division of Thales. And it's a machine that is capable of cooling down to 70 Kelvin just by consuming 10 watts. And the time scale of this cooling down is about 2 minutes. So super fast, very low energy needed to do that. So the fact that we focus on high TC superconductors, it actually opens the way to many applications, portable applications, embarkable applications, all sorts of applications where low TCs will not be allowing us to do this kind of step towards applications. So let's talk about them. Of course, as you can imagine, if you're talking about a high sensitive sensor that we can embark in a plane, in a boat, in a drone, we cannot talk about magnetic anomaly detections because it's a very sensitive magnetometer, so it can detect any disturbances caused by big metallic stuff roaming around and perturbing the Earth magnetic field, aka submarine. It can be used for other strategic communications and defense applications, but not only. Here I've given you 2 examples. But not only, because also there are applications that stem away from defense applications. We can use them in radio astronomy, on a very important field for squids nowadays, which is geophysics and earth-ground exploration, where we studied, again, the deviation from the Earth magnetic field to detect reservoirs of any mineral, maybe silver, maybe rare earth materials, anything you want. So you just, it's actually done nowadays with squids, where you hang a squid system down an helicopter and then you scan a very large area and you go look for reservoirs like this. But you can also use it for nanoscale magnetometry, where we can actually be sensitive down to the single spin due to the high sensitivity of these devices. But also more civil applications like medical imaging, MRI, for example. Here is something that we work in a collaboration with Bordeaux to actually use a skiff inside an MRI machine. And that's because nowadays the trend for MRI machine is to actually increase the magnetic field generated by the machine to improve the resolution. But there is a drawback, and it's the price. Because you can say that every Tesla that the machine has, it costs 1 million. So nowadays you get machines up to 9 Tesla. So you can see it's a machine that costs up to easily 10 millions. So not everybody can afford this kind of machines. So if you could be able to stem away from the classical antenna used in these systems and use actually a skiff, we will be able to have the same resolution, but with machines that have a lower magnetic field, so way cheaper. And other things that there is a field of research is for magnetoencephalography, where ITC superconductors, they actually allow you to be closer to the brain to actually detect the signal from the brain and do your MEG. Before we start with the fabrication, just a bit of water. So let's talk about how we fabricate them and our recent results. Why fabrication is important? Well, something I've omitted to say, or I've said not that much, is that of course all of this skiff importance and capacity of being a very high sensitive magnetometer, it only applies if you're capable of making hundreds, if not thousands, of junctions and squids with the same characteristics. So the loop area will be different, and that's okay, but the junction that will be they'll have to be the same. So they'll have to be working at the same critical current, at the same critical temperature. Otherwise, they will be contributing to the noise, but not to the signal, and that will be detrimental, because by increasing the number of squids, we will increase the signal-to-noise ratio. You can see that it actually scales as the square root of the number of squids. But of course, it only applies if they're all homogeneous. And as we will see in the next slides, homogeneity is pretty crucial and complicated to do for high TC materials because of their complex crystal structures. But it's something that we can tackle. Regarding fabrication, there are different techniques to make Josephine junctions. They span from planar devices to bicrystal to all sorts of things. I'm sure I've not listed all of them. And not all of them actually apply to high TC superconductors. So a few of them are only applicable only to low TCs, for example, like planar ones. We can do high TC planar junctions, but in a scalable way for SQUID and SCIF is not actually that convenient. The most common ways nowadays are either step edge or irradiated. And step edge is a little bit of an inconvenience, which is about the scalability and the freedom of the layout you can choose. And that's why in my group, we actually focus on the irradiated one, which is the one I'll be focusing in the next slides. So how do we make junctions with the irradiation? So it's all based on the principle that YBCO is a very sensitive, it's a material that's very sensitive to disorder. So whenever we change the crystal structure a tiny bit or the oxygen content into this complex crystal structure, the superconducting behavior of this material changes dramatically. This actually was studied in the early 90s already because of the interest that I was telling you on this kind of ITC materials. And it was shown that the decrease of critical temperature whenever we were increasing the number of displacement per atom in the YBCO is actually following the Abrikosov-Engorkov pairing law that you've seen written here, all right? Meaning that actually the increase of disorder inside, so the increase of disorder inside the YBCO, it actually acts as a depairing mechanism, depairing meaning that the Cooper pairs will actually be depressed in a more efficient way whenever we increase the defects. So the way we do that in a way to make junctions is to actually protect our conducting loop, except for the area where we want to create the junctions, and irradiate with very high energetic oxygen ions. So let's talk about how we do the fabrications in all its entirety. We start with a commercial wafer, which is a sapphire, which YBCO grown on sapphire and capped by a gold layer. Just by the first step is going to be just an optical lithography and an argon ion beam etching, just to define the contact pads. And in a similar fashion, we define the superconducting circuits. You can see here just it's a superconducting loop. It's not a SQUID yet because the junctions are missing, but that's what is done in this step. Again, it's an optical lithography where the critical dimensions is just 2 microns, so nothing too critical here. The critical stuff comes later on whenever we have to define the junctions. First of all, because we now involve E-beam lithography, where we define slits, so openings into the resist of just 40 nanometers, which is going to be our mask that's going to be used for irradiation whenever we flood irradiate the sample with highly energetic oxygen ions up to 110 keV. And you see that actually we create the defects only in the local area, in the narrow area where the slit of the resist is actually open. Here you can see an SCM image of one of the samples that we make here at the lab. You can see the resist, and that's actually the slits of 40 nanometer open all the way down to the YBCO film. And here you have the final results where you have the superconducting loop and 2 junctions on each side. And in this case, we created the S'(S) Josephine junctions, and the 2 of them making the SQUID. Of course, there want to be plenty more of them to make a SQUID, but that's the basic idea. As I said, this is the complicated part, especially the first part, which is the lithography itself. I know that this sounds a bit weird to say that 40 nanometers on E-beam is complicated to do because it's exactly what E-beams are used for. But usually this is done on resists which are thick only tens of nanometers. We have to do it on resists that are thick up to 800 nanometers. So that means that our expect ratios go up to 20:1. So it's a very big task to actually be done with the E-beam lithography. And especially it's a big task to be done in a way that is homogeneous on entire wafer on thousands of junctions that create the SCIF. But it's something that we can work on, something that we can control, and something that is a daily topic for our research. Here you can see the slim simulation where we show actually that the thick resist is needed because we have to protect the rest of the YBCO. If we want the junctions only to be locally whenever on these blue, light blue areas, we have to protect the rest of it. And protect means that the oxygen ions do not have to impinge the rest of the YBCO, otherwise we will lower the TC also on these dark blue parts. But nevertheless, we managed to do this. As I said, we deal with these difficulties on a daily basis, and we try to improve them throughout the time. Here you can see a few results that we obtained over the past in our lab. The publications are here down on the right. You can see that we obtain a skiff behaving, so devices with a skiff behavior with different configurations, and that we tested either in the range from 1 to 150 megahertz, and sometimes in other publications up to 1 gigahertz, with different configurations and with different sensitivity as well, and with different number of squids. But what is important to see here is like how it actually conforms to what I showed you at the beginning, how we make a skiff work as an antenna, because here you have in dark blue, in black, you have the skiff. Okay, that's the voltage against voltage against magnetic field with the typical anti-peak behavior. And then whenever you plot also the output voltage seen at the outside, at the output of the skiff, whenever there's an electromagnetic wave sent into the skiff with, for example, a power of minus 50 dBms and a frequency of 30 megahertz in this case, you see that the blue curve, so it's the voltage seen at the output of the skiff, it actually increases and reaches its maximum exactly where the skiff has its maximum slope. So it actually is a way of tracking the derivative, which is the red curve, of the VH curve. So it's a way to say that we are actually using the skiff to be used as an antenna, because we have this high reception here. The highest reception is actually at the highest point with the highest sensitivity in the VH curve. So this is about some results that we got on samples. Regarding sensitivity and homogeneity of the samples, we realized that we are a bit far away from what could be the absolute goal for this kind of devices. Especially about homogeneity, we realized that in huge differences between different ones, because again, it's very tricky to control the alien radiation, which again is a huge impact on the TC, on the change of the TC in the irradiated area, and also the E-beam part where actually we make the slits. So a huge part of our work is actually on improving the dispersion on this kind of devices. And for example, regarding the irradiation, an important measurement of it is the dose applied to each sample. And since our sample are made by deposited on top of an insulating substrate, plus they have a resist on top to protect the sample, the YBCO, from being irradiated entirely and not only in the junctions area, it's very insulating. And the way we measure nowadays the dose is actually by integrating the current flow into the sample. So that creates a not entirely reliable way of measuring the dose, especially between runs, especially between different samples. So we came up with another way of checking the amount of defects that we create inside of these devices, and it's by in situ and in real time measuring the change of resistance during the irradiation. To do that, we have these devices here that you see at the bottom right. It's something that we call the irradiation monitoring device. It's because we have just a bridge where at the center we have our 8 junctions, which is our way to simulate a skiff in a way, or to anyway to control the quality of the junctions made. And just next to it, we have this micrometric size window where we can actually measure the resistance during the irradiation. So instead of relying on the dose applied by the machine, which again can be not entirely reliable due to the insulating nature of our sample, we rely on the change of resistance that you can see here. That's exactly whenever the fluence of the dose increases, the resistance of this window increases. And then we can actually target a certain change of resistance from the initial value to the final value, instead of actually aiming for a dose which again can be different from sample to sample. So by applying this new technique, this in situ technique, and relying on the resistance change instead of just of the dose, we were capable of actually doing a study on the radiation, on how to improve the dispersion in radiation. And the study was actually making two sets of samples. A set of sample had a metallization layer on top of the resist to actually improve the ion irradiation, the charge evacuation during irradiation. And one was the classical way without any metallization layer on top. Then we took those devices and we measured two key parameters. So the TJ, which is the establishment of the Josephine coupling temperature, because whenever we do the RT measurements of those devices, we have the first transition temperature. Here you see in the derivative. You have the first transition, which is the transition of the electrodes. And then you have the transition where actually the coupling is onset across the barrier. And if you are lucky enough in a good sample, you can see that we have one TJ only. That means that the 8 junctions creating the device were actually pretty well uniform, and they were all having an onset of
Salvatore, we cannot hear you anymore. Hello?
Okay, sorry about that. It's difficult for me to know if I'm still online, so if it happens again, I'm sorry. Okay, let's start then again. So as I was saying, we made two sets of samples where we metallized the top resist in order to see if charge evacuation will improve and actually make an improvement in the dispersion of our junctions. And the other set was kept as is, so without any metallization. With the devices, we measured two key parameters, which was the TJ and the critical current. TJ is what we define the onset of the Josephine coupling, which is effectively the second transition that we see in the RT curves. Here in the derivative, it actually shows as two peaks. So you have the first peak, which is the TC, and the second one, which is TJ. And you can see that this specific sample, we were lucky enough because it showed some kind of uniformity and some kind of homogeneity because we had only one peak. But for example, for this one, homogeneity was not there at all because we had 3 different TJs, meaning that from the 8 junctions that we had in series, we had at least 3 sets of different TJs, so a pretty high inhomogeneity. The same was done for the critical current, where we measured the IV curves, and we defined the critical current as the peaks of the second derivative, so the gray curve here. And you can see that in the specific case, we had 2 values of critical currents, again, highlighting inhomogeneous junctions. From all these studies, we went ahead with a statistical analysis, because the junctions were over 500, the one that we measured. And already on the graph in the left, where we have TJ over TC, so it's normalized TJ over TC, you can see that the non-metallized ones, they have a very high scattering, very high deviation. There is no clear trend that can be evaluated from this graph. Well, for the metallized one, you can see that there is some kind of trend, this linear trend, and the scattering is way less pronounced. We went ahead and did this second statistical analysis where we just took these points and referred them versus the displacement per atoms as the Abrikosov-Gorkov law, which we actually fit. And we can see that with a clear agreement in both cases, but especially for the metallized one, we can see that the standard deviation was improving. It has improved a lot because we can observe an improvement in the dispersion of 3 times. The same kind of analysis was done for the IC measurements, and we could see that the improvement was 1.5. So just is to say that throughout this entire last part about fabrication, it's very crucial to control the creation of defects inside these oxides. And it's more crucial whenever you want to make a large number of skids to make a skiff out of it. And that charge evacuation plays an important role as shown here. So, for example, in the same approach, in the same kind of line of thought. We are applying a change in the fabrication process, where actually instead of making the Josephine junctions on an etched YBCO, where actually there is a very tiny amount of YBCO with just the superconducting circuits, we make the junctions on a plain YBCO, so we invert the optical lithography steps in order to have the YBCO, which is still a bad conductor at room temperature, but still a conductor, that can help actually the evacuation of the charges during the E-beam lithography and the radiation. And this actually is proving to be a good choice because we're observing very good results that hopefully will be showing in the future. I think that was the end of it. I'm sorry again for the interruption for the connection. Hopefully you are still there for my conclusions. By concluding, I'd like just to say that we talked about the quantum interference antenna, which is a device, as a SCIF-based device with high TC superconductors, which is capable of being an ultra-wideband sensor. And since it's based on high TC, we can actually envision to do miniature cryocoolers. You can see this nice mock-up of what it could be in the future. And that our fabricated Josephine junction by Agni radiation, that they showed an operation up to gigahertz regime. We talked about the technical challenges that we face to improve the dispersion on these kind of junctions, and the dispersion improvement that we put in place throughout the years. That was it. Thank you so much. Hopefully you're still there.
Thank you very much, Salvatore. Yes, we are here. So I see that we have a bunch of participants from all the nodes of the consortium, Munster, San Sebastian, Madrid, and some from outside also. And now it's time for you to ask questions. So I see already a hand which is raised. So please, Clara, Sara Catalano is, for a question. Please, Sara,
Hi.
I think your mic should be open.
Yes. Can you hear me?
Yes.
Okay.
Yeah,
thank you for the beautiful talk. I wanted to ask regarding this measurement, very nice, of the squiff, which you also show in this last slide. I didn't understand at which temperature is this measured?
Wait, you're talking about this one, the skiff here?
Yes.
That's a good question. I think this specific one must have been around 65K.
Okay, thank you. So you are operating at the at high temperature, let's say.
Yeah, absolutely. Yeah.
Okay, thank you.
I mean, not to 90K, of course, because we have to be in the regime where actually the below the TJ of the junctions, but still no, absolutely way higher than low TCs. Yes.
Yes, and incidentally, let me ask you this question. This small cryostat you presented, it goes down, I don't know if you said it, I don't remember, to what temperature? Because this is operating at 65, so this is a small cryo cooler that you can hold in your hand. How long can it go in temperature and how fast?
Well, there are different kind of models, obviously, and they all have a different cooling power. The really small one that I showed you, because it's the one that catches everybody's eyes, it goes down to, I mean, depending on the charge loads, but it goes down to 60 Kelvin easily, yeah.
Okay, so you could operate this squid in this small, this skiff in this small price.
That's the idea. Then of course it's gonna be, I mean, it's just not a squid by itself. You know, you need to polarize it in current. You need to polarize it in magnetic field. There's gonna be a few elements around it. You will need to have the rest of the RF chain, so amplifier and whatnot. So maybe the volume will not be exactly the tiny one that I showed you, but something that we think is gonna be in the order of liters. Yeah.
Okay, from the cryonic point of view, is feasible. Okay, now there is Andrei Masanik from CSIC who is asking a question. Hello, Andrei.
I have a couple of questions. First, I understand that your scheme measures actually magnetic field from a signal. My first question is, how does electric field of electromagnetic wave will influence to the transport through such schemes which you had? And second question is, I guess you have to use synchronization between different Josephine junctions, different squids to see your signal and so on. How do you control the synchronization? Thank you.
So I was hearing you pretty badly, so sorry if my answer will not be on point, but I'll try my best, otherwise I'll ask you to repeat it. So regarding the first question, yeah, of course, the electrical component of the electromagnetic wave might induce some parasitic currents. It all depends on how you configure your reception line, obviously, but you can get away with it by just moving the skiff in a different orientation and avoid the electrical component of it. Regarding the synchronization, I'm not sure I understood, because whenever well, I think it's part of the challenge of making this kind of device. If you make sure that the junctions are uniform, then in the entirety of your line, which is pretty long sometimes, then there's going to be a question of synchronization. It's just a matter of being at the same current and at the same temperature. So it will be actually all relying on that. Hopefully I replied to your questions.
It looks so, because
Yeah.
he went. Wait, is the yeah? Sarah is asking a question again. So please,
Yeah.
Sarah.
Hi. Yes. So I have another question regarding the role of disorder. Do you have some estimation of so what is the tolerance, let's say, to the variation to the critical? So I mean, identical, it will never be. So a little bit it must change. So how the efficiency goes with the variation of
it's a good question.
current?
It's a question that we. It's a good question. It's a question that we ask ourselves, and that's why we put in place some simulations on it. We're in the process of actually setting up some simulations on the topic to actually realize what is the limit of this. Yeah, absolutely.
Thank you.
Okay, now we have Sebastian Bergeret from CSIC.
Yeah. Hi. Thanks, Salvatore. Beautiful talk. Very nice talk. I have a question regarding, I think we had some discussions some time ago when we think on YBCO and these unconventional superconductors. Now we have this anisotropy and so forth. How important is that in growing your samples, or that is not important at all, and the transport goes, let's say, in, I don't know, in which axis it goes, or is there something that you have to take into account when you build your huge samples with YBCO about this anisotropy, that intrinsic anisotropy of the superconductivity?
Hi, Sebastian.
Yeah.
I don't think it's actually that crucial for these kind of junctions. For the other ones that we make for redox and all of that,
yes,
I think it's going to be an important side. But for these ones, I mean, to be seen, because we only use the C-axis one, and it's the one that actually gives you the most, how to say, sensitivity to the ionizing radiation, actually. So yeah, to be seen.
Okay, thanks.
Okay, Andrei, I think he wants to ask another question.
Andrei is back.
Yes.
Andrei is back.
Another question.
Can you talk a bit louder? Excuse me, Andrei, because we.
Yes. Another question. You rely on YBCO, and it is kind of obvious that using YBCO one could form anisotropy, intrinsic anisotropy of Josephson of superconductors in such a way that the Josephson junctions will be in this 2-phi current phase relation. My question is, could you create on a scheme a lot of such 2-phi Josephson junctions in URI, for example, to use their intrinsic, let's say, multi-stability?
Sorry, Andrea, I didn't catch that. Can you repeat that? Really, it's still difficult for me to.
I think he's asking about the.
If you catch that,
maybe I can. I think he's asking. Correct me, Andrei, but I think he's asking about exploiting the D wave, character to use like I junctions or things like that. This is what you're asking.
2-phi junctions inside the schemes. Yes, exactly.
Yeah. Whether you can exploit this somehow.
But then in that case, you will have the issue of the scalability. You have to remember, we go through this path just because of the scalability. We have to make thousands of them, and we go through the pain of this doing any rotation just because of that. With your way of seeing things, I'm not sure then scalability will be an issue. It's going to be interesting from the fundamental point of research it, but from the scalability and making skiffs, it's going to be a challenge even not doable.
But no way it will become doable in some time in future.
Well, who knows?
Okay, thank you.
Okay.
Anytime.
Yeah, and you still have your hand raised. This is just your hand stayed raised, or you raised it again? I guess he raised it again. It was from before. Okay, so there's no more question from Sebastian. Okay, so I have one final question, which is for my side. I say maybe there's others. Ion irradiation is so you use mask ion irradiation to kind of pattern your junctions. Is there any? I mean, is this better, or can be this improved otherwise using focus ion beam or related techniques? I mean, are there people doing this, and what is the advantage or disadvantage versus mask ion irradiation for doing this?
Yeah, good question. Yeah, I mean, I forgot to mention them because again, there are many techniques, and I didn't have time to go through all of them. But ion irradiation, it's a way to make Josephine junctions, and masked ion irradiation is a way of making them. The other way is actually to make them by direct writing with a focused ion beam, as you said, Javier. But although the results are very promising, there are some groups and our collaborators at SPC that they use it. The only drawback is that you are obliged to write every single junction one at a time. Yeah. So we're back to the problem number one, which is scalability.
Okay.
I think we tried to talk to the people involved in the technological aspects of this to implement a moving stage in order to automatize the fabrication of this kind of devices by focusing on beam. But at the moment, there are no commercial availabilities, and there is no way to do it. So
it's not as fast. Yes.
Yeah. You will have to write one by one, and when you're talking about thousands of them, it's not practically viable.
Okay, thank you. Jacobo is asking a question now. Jacobo, please go ahead.
Yeah. Thank you very much. Can you hear me?
From Complutense.
Yeah, I can. Hi, Jacobo.
Yeah. Thank you, Salvatore. Great seminar. I have a question. Maybe it's a stupid question, but when this describes the squids connected in parallel, how do you prevent that the branches from neighboring squids form another squid that gives you an additional signal?
Good question. Yes, but it's something that we've. 2D squids is something that we always wanted to explore, especially because you can play around with the number of squids in series and parallels to lower the impedance, for example, in order to have a 50 ohm impedance. But we never actually used them so far. But of course, your question is good, and I think the way to get around it is a way you make the layout, and then we've just a question of making a good layout that prevents for this issue. Yeah.
Thank you very much. Thank you.
Anytime.
Okay, any other questions? You can take the opportunity now to ask Salvatore. Just as a reminder, this video will be posted at some point in the webpage of the project. And of course, because Salvatore is a member of this consortium, you will be able to just drop him an email eventually if some of the questions come to your mind later on. But there's now time still for another. Jacobo, you have still a question, or it's just that your hand?
No,
okay.
Maybe no. It's my yeah.
Okay.
Thank you.
Good. So if there is no more questions, I think it's time to thank Salvatore for this very, very nice seminar, which made very clear how these quantum antennas work. It was a nice reminder of Josephine physics, and he also put us to date on this high TC based technology, which is being used. It's not like a prospect. So this is very nice. Thank you very much, Salvatore, again. Thank you all for coming to this seminar, and see you next one, which will be probably in late spring in the month of May. It will be announced in due time, and see you. Thank you very much.
All right. Thank you, everybody.
See
Bye
you.
bye.
Thank you.
Bye bye.